Hello all, welcome to the last session of IWQC 2020, titled Mostly Routing. I'd like to introduce Lingling Lao, who will be talking on timing and resource-aware mappings of quantum circuits to superconducting processes. Take it away.
Thanks, Seth, for the introduction, and thanks everyone for coming. So my name is Lingling, and this work was done during my PhD at QTech, and currently I'm a postdoc at UCL. So just give you a little bit of motivation about this work. There are many hardware constraints in NISQ processors, and quantum applications needs to be compiled to adapt to these constraints, including the primitive gate size. For example, the most of the current quantum processors only allow single qubit rotations and one or few 2-qubit gates. For example, the Service 17 superconducting processor that is being developed at QTech only allows C-fifth gate. And it means high-level application gates needs to be decomposed in this available gate size. And furthermore, quantum technologies such as superconducting qubits and quantum dots arrange qubits in 1D or 2D arrays with nearest neighbor interactions. For example, the red figure shows the topology of this Service 17 processor, where the dots are the qubits and edges are the possible connections between qubit pairs. And because of this limitation, routing will be required to route qubits to be adjacent for 2-qubit interactions. And moreover, classical control electronics are used to control and operate qubits. However, a dedicated instrument per qubit is very expensive and not scalable. Therefore, classical control electronics will be shared among qubits for large-scale quantum processors. For example, 8 qubits are using the same readout line in the IBM Hummingbird processor. So prior works have proposed different compilation passes to deal with these constraints. For example, the decomposition optimization that decompose gates into native gate size, and qubit initial placement and the routing that minimize the number of swap operations, and also gate scheduling to minimize circuit depths for decoherence limitation. And also, some of these works also propose noise adaptive strategies to exploit the noise variation across qubit and gates, across qubits and time. However, most prior works, they do not consider gate duration and classical control constraints. So our work will take this into account and develop compilation passes such that quantum operations can be performed at precise timing and also allow valid execution of quantum circuits. So in particular, we focus on the classical control constraints in this Service 17 processor. And in this processor, single qubit gates are performed by using microwave pulses. And these pulses are applied at a few fixed frequencies. And we assume that qubits in the same frequency share the same arbitrary waveform generator. And the consequence of this control constraint is that the qubits that are sharing the same frequency can perform the same type of single qubit gates. However, different type of qubits, different type of single qubit rotations cannot be performed in parallel on the same frequency qubits. And the measurement is performed by using phase lines in this processor, and each phase line is coupled to a few qubits. And because the measurement is realized by several steps in sequence, and the readout of one qubit cannot start if the other qubits that is coupled to the same phase line is being measured. So this shared classical electronics of single qubits limits the parallelism of single qubit operations. And furthermore, for the 2-qubit gates, a C-phase gate on this processor is realized by bringing their frequencies close to each other. For example, if we want to perform a 2-qubit gate between qubit 2 and 3, we can lower down the frequency of qubit 2 to its interacting frequency f1, which is close to f2. However, we have to be careful that interactions will occur on any connected qubits that have close frequencies. For example, if we want to perform an interaction between qubit 2 and 6, we will have to detune the frequency of qubit 5 away, such that we will not end up with an undesirable configuration. And similarly, we can also not perform the interaction between 2 and 6 and the interaction between 1 and 5 in parallel because of this 2-qubit gate control limitation. So all these constraints limit the parallelism of 2-qubit gates and also single qubit gates. And more importantly, violating any of these control constraints will result in invalid execution of quantum operations. So our work proposed to formulate classical control constraints as resource constraints in a conventional list scheduling algorithm. And we use lookup tables to describe the constraints of a single qubit gate. So we describe the number of AWGs and also for each AWG, the list of qubits that are using this AWG. And we also use one lookup table to describe the number of phase lines and also the list of qubits that are coupled to this phase line. And for the 2-qubit gates, we use 2 tables to describe the control resources. And we use 1 table to describe for each connection which other connections cannot be used. And also, we use another table to describe for each connection which qubits have to be detuned away to avoid unwanted interaction. And we define a machine state to describe the status of each resource. And each resource state is defined by its occupied operations and also corresponding occupation period. And so to implement this list scheduling, we first construct a quantum operation dependency graph where each node represents one operation and each directed edge represents the dependencies between these 2 operations. And the weight of edge represents the gate duration of its predecessor. So for our list scheduling, we first initialize the resource states where all the resources are available at the beginning, and then we find all the available operations in this dependency graph at cycle t. So an operation is available means that all its predecessors have finished at this cycle. And then we check the resource availability for each available operation. And afterwards, we schedule the resource available and the most critical operation at cycle t. And then we update the resource state and also the available operation set at cycle t. And we repeat step 2 to 5 for cycle t until no operation can be scheduled at this cycle. And then we move on to the next cycle. So the time complexity of this resource-constrained list scheduling scales polynomially with the number of gates. And for example, if we want to execute this circuit on the CV17 processor without the described classical control limitations, so after the initialization at cycle 0, we find the available operations are x1, x2, y0, y3. And then, as we know, our resources are available at this cycle. So we find out that x2, x1 are the operations in the critical path. Assume that we schedule x1 at cycle 0, and then we update the resource state S, where frequency f1 is occupied in the period of 0 and 1. And then we will update the available instruction set. Similarly, we can schedule x2 and y3 at this cycle, and frequency f2 and f3 are occupied in the period of 0 and 1. However, we cannot schedule y0 at this cycle because of the control, the single qubit control constraint. And because f1 is already occupied by an X operation, and we cannot perform a different type of single qubit gate anymore using frequency f2. And also, we cannot perform y0 with C0, 1, 2 at the same time, even though they don't have any dependencies in the dependency graph. This is because of the 2-qubit gate control constraints. And if we assume we have already scheduled C0, Q1, and Q2 at cycle 0, then Q0 will, in the resource state, we will say Q0 is occupied by C0 because we have to tune the frequency of Q0 to its parking frequency because of the control constraint. And similarly, we can also not perform C0 2.4 and C0 3.5 at the same time because of the 2-qubit gate control limitation. So we have developed a compiler to be able to compile quantum circuits to hardware-constrained devices. And the objective of our compiler is to minimize circuit latency. And it takes into account the native gate set, the chip topology, and also gate duration classical control constraints into account. So we implement the resource constraint scheduling in both routing and scheduling procedure. And for the routing heuristic, it first finds all the shortest path between two neighboring qubits, which is similar to the other routing works. The objective of the parallel routing approaches is to minimize the number of swap operations. And furthermore, we evaluate all the possible movement operations for each shorted path, and then we choose one site that will minimally extend the circuit latency. The time complexity of this routing heuristic scales sub-exponentially with the number of qubits in the device. And for example, we want to perform a C0 gate between qubit 0 and 3, and we have like such a initial qubit placement. And there are multiple paths between qubit 0 and 3. And for example, we can swap Q2, Q3, and Q0 and Q4. However, because of this 2-qubit control limitation, these interactions cannot be performed in parallel. And alternatively, we can swap qubit 2, 3, and swap qubit 0 and 1. And this set of movement will not violate any hardware limitations. So the routing heuristic will choose this set of movement because it will lead to a lower latency overhead. So we evaluate our Qmap compiler and compare it with other compilation strategies that do not consider the control electronic constraints in the routing procedure. So one is called mini-path compiler that chooses shortest path and one set of movement operations without evaluating which one will lead to lower circuit latency. And another one is a base compiler, which do not apply any circuit optimization and also doesn't use any qubit initial placement. So the trivial compiler, the complexity of the root scales linearly with the number of gates. And our compiler Qmap has the highest time complexity. So to compare these different compilation strategies, we analyze their latency overhead and also their gate count overhead. So from these two figures, we can observe that the mini-path compiler has a lower overhead compared to the trivial compiler. And our Qmap compiler has least overhead compared to the other two. And compared to the mini-path compiler, Qmap has around 22% latency reduction and 3% gate reduction. So to conclude, classical control electronics will be shared among qubits in scalable quantum processes, which will limit the parallelism of quantum instructions. And resource constraint scheduling can be used to comply with these control limitations and also minimize circuit latency. And the Qmap compiler can outperform the other compilation strategies, but with sub-exponential time complexity. So future work will focus on the optimization of the heuristic such that we can reduce the time complexity. And thank you for your attention.
Thanks, Lingling, for a really interesting talk on bringing new constraints into the typical routing program. I'd like to remind everyone that there is a Slack channel where you can ask questions in. I do have a question for you, which is that you kind of fairly intuitively, one would expect that by reducing the total circuit latency, the resulting circuit you produce should run more effectively on a quantum computer. But I have seen other works in which they try to use gate fidelities to improve their routing heuristics. But ultimately, the metric they use doesn't actually accurately predict which swap paths will improve circuit performance the most. So I was wondering if you'd had a chance to actually run these scheduled circuits on a real device and see how the performance compared.
Yeah, good question. Thanks. So because currently we haven't run any real experiments on the real devices, because like, for example, the IBM's devices, they do not have this classical control limitations. So we only done some numerics. But I think our work are compatible with this fidelity aware compilation like heuristics.
Okay, yeah, I guess that does make sense. Thank you. Another question I had was also how extendable this method could be. So an example is there are several routing heuristics available in common quantum softwares like Qiskit or also PyTicket, and whether one could easily apply the swap routing heuristics from these methods into your approach to maybe ultimately improve the latency you find.
Yeah, I think it will be compatible. So like for our routing like heuristic, like the first part is similar to the prep works that we want to find like a path that we can swap our qubits. So, and then our work is based is on top of that. So for each path, we evaluate what are the swap operations we should use to reduce the latency. So just increase the complexity of this routing procedure.
Okay, thank you. There has been one question, though I think it's fairly similar to mine, but Ross Duncan asks, since your comparisons are against other algorithms which don't respect the control constraints, did you also compare against other routing methods?
So yeah, we didn't compare with other routing methods. So in the evaluation, maybe I didn't explain it clearly. So what I mean about other compilation strategy is that they do not consider the control constraints in the routing procedure, but they will take this into account in the later parts. So we assume that this will be taken care by another scheduler, and which is also included in our simulation. So what we are comparing is if we consider these constraints in the routing, which is a Qmap, and if we do not consider it in the routing, but we do it in a later part, which is other compilation strategies. And we show that it's better to consider it in the routing procedure if you really want to reduce the latency overhead. However, with the cost of the time complexity.
I guess there's no further questions yet. I guess another thing that might be interesting compared to is that obviously ultimately you're trying to reduce the total circuit runtime, but it might be interesting to see how routing algorithms that maybe don't consider time constraints, that do have some qubits left idle when they finally route the circuit, if whether you could apply sequences of gates that actually have the unitary of the identity on idle qubits, and whether that can that kind of combination of smaller swap overhead plus idle qubits having kind of a amplitude damping error reduced, whether that combination might compare to the gate errors found in the kind of minimal latency case.
Yeah, so I think in the literature, like there's some papers talk about like applying, for example, dynamic decoupling on the idling qubits to reduce like crosstalks or other errors, which will improve the application performance. That's indeed a very good direction to go. Yeah.
I think that'd be an interesting comparison to see. There has been another question from Seon Sivaraja, who asks, this might just be something I missed, but is the control setup you show related to the Google processor setup?
Not really. It's a setup of a processor that is being developed at QTech, Delft University of Technology.
Could we speculate that the Google processor would have fairly similar constraints, though?
So we would expect that for like large quantum processors, there will be some similar control constraints because it's not possible to use one dedicated like electronic to control every qubit. Assume that like we have 1,000 qubits, right? The varying and the crosstalks will be terrible.
Yeah. I guess it might be interesting to see how these constraints vary from computer to computer and how we have to change scheduling solutions for them. But would you expect that maybe the constraints should be similar enough that we can use a similar approach for each?
Yeah, I guess no matter what kind of like classical control constraints they have, probably we could use similar approach to formulate them into resource constraints. So we can use this this scheduling. Yeah.
Okay, well we're definitely out of time anyway, so thanks again for a great talk.